and you can see his title on the screen. So thank you, Hubert.
Thank you very much, Claudio, for the invitation. So what I'm going to talk about is joint work with Quentin Berger from Paris and Karsten Chong, who is currently in New York. And I'm going to discuss the stochastic heat equation with multiplicative Lévy white noise. So, okay, let me first present the equation. So the unknown is a function of space, space and time. So time is r plus, space is rd, and the evolution of u is driven by two things. So first you have a diffusive term, okay, 1/2 of Laplacian of u. And then you have a multiplicative term, which is beta xi times u, where beta is a positive parameter. Xi is a Lévy space-time white noise, and the multiplication here has to be taken in the Ito sense. And for simplicity, we are going to consider in this talk the case of where the initial condition is Dirac at 0. So I'm going to come back to this and okay, explain a bit more about well, the definitions. But first, I want to give some motivation for this problem, and at least the reason for which Quentin and I started to work on that. So Karsten is specialist of SPD, so he didn't need any motivation, but we did. So our motivation came from directed polymer. So let me try to say something about directed polymer. So it's directed polymer model is a modification of the simple random walk on ZD, which is based on a random environment. So you consider an IID random field, which is indexed by discrete time and space, so by n times ZD. And you defined a new measure on the set of trajectories, which is absolutely continuous with respect to the simple random walk, and whose derivative is proportional to exponential beta times the sum of the etas along the graph of your walk until time n. Okay, so you're considering the graph of the walk and not the walk. So this is why the model is considered as directed. And here Z is the coefficient of proportionality you need to apply so that this thing is as expectation 1. And well, this is called partition function. I will refer to it as a point-to-line partition function. We'll see that in a moment. Okay, so if you just look at the first n step of your random walk, okay, and you look at this distribution under the polymer measure, what you have is that the probability of each trajectory is proportional to the product of exponential beta eta, where you take the product along all the sites visited by the graph of the random walk. Okay. Okay, so what I want the reason why I'm talking about that is because stochastic heat equation is somehow, in a sense, okay, very roughly speaking, a continuum version of this directed polymer model. So let me be a bit more precise about this. So okay, let's try to just define a continuum analog of the model I just presented. So for simplicity, consider first a continuous bounded potential, okay, indexed by time and space. And we define the continuum analog of the polymer measure we had before. So it's we replace random walk by Brownian motion. So it's absolutely continuous with respect to Wiener measure. And now the derivative is proportional to exponential beta times the integral of our potential along the graph of the Brownian motion. Now, okay, we have this renormalizing factor, which is expectation with respect to the Wiener measure of this exponential. So this is the point to line partition function of the model. We can also consider the point to point partition function, where instead of taking expectation with respect to Brownian motion, you take expectation with respect to the Brownian bridge. And the idea is to look at the contribution to the partition function of trajectories that end up at X. Okay, and well, to do that, actually, the sensible thing to do is to multiply also by the Gaussian heat kernel in front. Okay, so rho Tx is just well, the density corresponding to a Gaussian variance. Okay, so this point-to-point partition function, it's related to the point-to-line partition function. You just get the point-to-line partition function by integrating the point-to-point partition function over space. It describes the probability distribution of the endpoint of your Brownian polymer, if you want, because well, the probability density of BT under the polymer measure, it's given by the ratio of point-to-point over point-to-line partition function. And more interestingly for us, Z is the solution of this equation with multiplicative potential. With Dirac initial condition. And the writing of this solution as an expectation over the Brownian bridge, it's called the Feynman-Katz representation of the solution. So, why do I consider a problem with Lévy space-time white noise and not a nice potential V? Because it seems easier. Well, polymer, for the discrete polymer model, we had an IID environment. And of course, the only analog of IID environment in the continuum is space-time white noise. So this is the sensible thing to do. Okay, so now I guess there are many people in the audience that are not specialists with SPD and noises. So let me give an easy definition of Lévy noise, and which I will also use then in the remainder of the talk. So so let's first our first ingredient to define the Lévy noise will be a measure lambda which has support on R plus, and I assume that it's integrable at infinity and that Z is integrable at 0. And well, in order to construct a Lévy noise from this measure, what we do first is consider a Poisson point process on a space which has 3 coordinates. So these coordinates are time, space, and the third one is jump intensity. And then from a realization of this Poisson point process, we define a random measure in the following manner. So for each point of the Poisson point process, we place a Dirac mass whose location is given by the 2 first coordinates of our point, and we put in front an amplitude which is given by the 3rd coordinate. And we take the sum over all points in our Poisson point process, and this gives you a locally finite measure because of this assumption here. Because of these 2 assumptions, if you want. And for a reason that will become obvious on the next slide, I decide to subtract a constant. So I'm writing this as a measure, so I'm subtracting a constant times Lebesgue measure, and this constant is simply this integral, and it kind of compensates the jumps of amplitude smaller than 1. So that these things will have average 0. This random sign measure is what I will refer to as a Lévy space-time white noise on quite improperly. So this is the reason why I say I will refer to as the Lévy space-time white noise with jump intensity lambda. So in fact, you can define Lévy noise under more general assumption, and this is as general as we will get. So still consider a measure on R plus, but this time you only consider that Z2 is integrable at 0. So possibly your measure can have heavier weight around 0. you just do the same thing, but we are going to use a truncation procedure. So given positive A, okay, what we do is the same thing as before, except that we only consider points that have jump amplitude larger than A. Okay, and we do the same thing as before, and in the constant we subtract, we just integrate from A to 1. Okay, and what happens in this case is that, well, this sum here, when A goes to 0, okay, it's still a well-defined measure, but it becomes locally infinite, so it's not very. But at the same time, kappa A diverges to infinity. And it turns out that these things exactly compensate one for the other. And under the assumption that Z2 is integrable at 0, which is an optimal assumption, you have a convergence towards a non-trivial limit, which is, okay, what is the Lévy spacetime white noise with jump intensity lambda. Okay, and this convergence also holds in a space of distribution, so in a Sobolev space of a local Sobolev space with negative index. Okay, so I mean, I could have said shortly, I mean, Lévy spacetime white noise is just the d-dimensional generalization of the derivative of a Lévy process, but okay, I guess this was a sweeter, maybe a more accessible introduction, and I will use this construction with truncation in the remainder of the talk. Okay, so this is not the most general definition you can find. So, for instance, here I'm considering only positive jumps. Some of our results are true even if you consider lambda that has support on R, but the connection with directed polymer only remains if the jumps are positive, okay? Because if not, the partition function will not be positive. So another thing is that I'm not considering Lévy noise which have a Gaussian white noise part. So this is a lack of generality. Okay, but I don't think this is a big one, because in any case, our solutions would not be defined in dimension 2 and more if you have a Gaussian part, which is included. We will come back to that in a second. And the third thing is I fixed in a kind of arbitrary way the constant part of the noise. Of course, you can always add a constant, but it wouldn't change very much to the solution. It just corresponds to an exponential factor in time. So okay, so these are the three restriction I have, and okay, B is the most important one if you want. A and C they are just there for simplicity of exposition. And a particular case that we are going to be interested in is the case of alpha stable noise, where the lambda has density, which is a pure power, okay, with an exponent alpha, which is between 0 and 2. Okay, so what's the aim of the talk, what I will try to do today? The main result I want to present is necessary and sufficient, or well, okay, a necessary and sufficient condition that almost match for the existence and uniqueness of solution to this equation. Then there are two things that I will try to discuss if I have enough time. So first one is how the solution to this equation can be obtained as the scaling limit of a directed polymer model in the case of where the noise is alpha stable. And the third thing is well, some result about localization of solutions. Okay, and I will say more on that if I have time. Okay, so first thing before starting, I have to maybe give a definition of what a solution to this is. So we are going to say that U is a solution if for every T and X we have the following almost sure identity, and okay, and where this is really a stochastic integral. So this is something which is well defined. And okay, the connection between this and that is really, well, you integrate with respect to time and you do some kind of formal integration by parts. So there is not so much hidden there, but just to tell you what we are checking in practice when we say that U is a solution.
Can a question?
Yes.
I don't. Is rho still the Gaussian density?
Yes, yes, yes.
Oh, good. Thank you.
Thank you. Are there any other questions?
Not for the moment.
Okay. Okay, so the first thing I would like to do is to kind of write a candidate expression for the solution, and maybe what we can do is start from the Feynman-Katz representation in the case where we have a smooth potential. So okay, the problem is that in that expression we have an exponential, and well, if you take an exponential of the integral of a noise, okay, this is going to be a bit tricky. So, but what you can do is look at the Taylor expansion of this, because then you, well, if you do that, then you don't have exponential anymore. So you get an integral to the k in the power expansion, and this integral to the power k, you can rewrite it as a k-fold integral. And then a second thing you can do is to say, okay, I can restrict this integral to the simplex. So I restrict the times that the time S1, I enforce the restriction that the times S1 to Sk are ordered. And by symmetry, this just makes me lose a factorial k, okay, because I have factorial k possible ordering for the indices. So therefore, if I just multiply by factorial k, I just get the previous integral, but this factorial k just cancels the one I have here. Okay, so here, if I replace this by the integral on the simplex, I will just cancel out the factorial k, and I will get this expression. Okay, and this is going to be okay. Then we are going to integrate with respect to linear measure, but this expression you can replace v by xi, and this is going to make sense. So maybe I want to give you a second justification for this expression. So the reason why you have an exponential in the Feynman-Katz representation is because of the multiplicative part. And really, this exponential here, it has to be interpreted as some kind of infinitesimal product of 1 plus beta v from 0 to t. Okay, whatever this means. But if you formally expand this is the expression you find. Okay, you just while this equality here might not be true if you have a v that starts to have to be less regular, somehow this identity is always formally true, and this is okay. This is a okay. In a sense, this makes more sense than this exponential. Okay, so okay, you can take it or leave it. I mean, it's just some explanation why this expression appears. Okay, so okay, so one thing you have to do after that is to integrate this with respect to the Brownian bridge measure and multiply by the Gaussian kernel. And in the end, what you find is well, a sum of integrals, and what you're integrating is well, the product of the v along the space-time points you visit, and you multiply it by a product of rows, which just corresponds to the probability density of visiting all the space-time points, which are your variables of integration, plus the last one, okay, which is your ending point. And this is going to be our candidate for solution. So I just replace v by xi. I introduce a notation for the product of rows that I had before, okay, and okay, our work will be to try to give a meaning to this, okay, to check that these multiple integrals can be well defined and that they are indeed solution to the equation. So let me first talk about the case where xi is a pure Gaussian white noise. because this has been much studied in the literature, in particular because it has connection to the KPZ equation. And in dimension 1, everything works well. All your integral, I mean, the iterated integrals, they make sense as Ito integral. You can compute the L2 moments, and if you sum everything, you get something which is bounded in L2. So this expression makes sense, and it is a solution of the stochastic equation with initial condition, which is Dirac. And this has been known since the 80s, and you can find it in lecture notes of Walsh. But as soon as you move to dimension 2 and more, you get into trouble. So and it's not very difficult to see. So so the expression does not make sense formally, and you can see just by looking at the term k equal 1. So the term with k equal 1, you're just integrating a function against white noise. So it's a Gaussian variable. Okay, so therefore, if the variance is infinite, it's not something that is well defined. Okay, it's not possible that it's a variable with infinite variance. It's just a Gaussian with infinite variance. So it's not well defined. Actually, this is not the end of the story, and people have tried to make sense of stochastic heat equation with Gaussian white noise in dimension 2. But in order to make sense of things, you have to apply a specific procedure. So you have to modify the noise, and while you're sending your epsilon in your modification to 0, you have to tune down the intensity of the noise to obtain a non-trivial limit. And this non-trivial limit is only in distribution. So there has been a recent breakthrough result by Caravena, Sun, and Ziguas, and it was a continuation of works that started in the 80s. Well, you just have to remember that this thing is really a different game, and this does not correspond to the type of solution we are looking at here. Okay, and there are okay. So this is about dimension 2. In dimension 3, there are also other works which are also following, in a sense, different rules. Okay, if you want to look at true solution, you're really restricted to dimension 1. Okay, so now let's get back to the case of Lévy noise. And okay, for the same reason as before, in dimension 2 or more, it's kind of difficult to check if this multiple stochastic integral is well defined. And the reason is that what's easier to do in stochastic calculus is to do L2 computation. And for the same reason as before, here things are not bounded in L2. So the approach we took, instead of looking at things in LP and trying to, is to consider truncated noise. Okay, so only jumps with amplitude larger than A, and then make the truncation level go to 0 and see if we obtain a limit. And when you have a truncated noise, this psi here is a measure. So you can consider this not as a stochastic integral, but as a measure theoretical integral. Well, you just have to check that these integrals are absolutely convergent. So, okay, let's see what we can do in this setup. So, okay, if you want to check that these things are absolutely convergent, what you can do is, okay, here in this psi A, you have two parts. So you have a part which is made of jump, which is positive, and you have a part which is the Lebesgue measure part, which is negative. And okay, at least on the formal level, what you can do is integrate first with respect to the Lebesgue part. And if you do so, what you obtain is exactly the same expression, where the noise is replaced by the positive part. But the thing that has changed is that you have an exponential term in front. And okay, that's convenient because it tells you basically that this thing is positive, and the only thing you have to worry about is that it blows up. So you only have to check finiteness. And this step is in fact rigorous. It's not difficult to show that this thing is finite if and only if what you have here is absolutely convergent. Okay, so if you were wrong in this step, it's because this thing is actually not well defined. So this is not something to worry about. So then you have two questions. Okay, I think the easier one is to check whether this thing is finite or not once you fixed A. And the second one is to know whether you have a meaningful limit when A goes to 0. So let's go through the first question, which is also the first result. So proved with Quentin. And we obtained a necessary and sufficient condition to have finiteness of the partition function. Okay, and the criterion does not depend on A, so this is fortunate. And okay, it's the following: you want log z to the d over 2 to be integrable at infinity. Okay, and so from now on, we are going to assume that this is okay. This the log and the 1 over 2 here come from the Gaussian density, and come from the dimension. It's not very mysterious, but it's okay. Okay, this is not difficult to check that this is necessary and sufficient condition for finiteness of the first term in K. There are some more works to show that this is actually sufficient for all terms, for finiteness of all terms. Okay, so from now on, we are going to assume that lambda satisfies this and look at the problem of the limit when A goes to 0.
Can you explain a bit more this condition, why it pops out? Or?
Okay, so you can look at the first term here. So you have integration of a heat kernel and you integrate the noise. So basically, when you integrate this, you want to make sure that the maximum of rho s. Okay, let's forget about point to point. Let's talk about point to line partition function. So there is no tx here, and you have only one point. K is equal to 1. So you want to know that if you sum rho sy amongst all the atoms of the noise, you want this to be finite. Okay, so you want the weight of the atoms to decay at least not to increase faster than exponential t square. Okay, and if you put this into Borel-Cantelli, okay, the weight of the atoms not growing faster than exponential t square is exactly corresponds to this. Does it make sense?
Yes, thanks.
Okay, and then basically the content of the result is that things do not get. You cannot do better than that if you consider groups of several atoms or things like that. Okay, so now if you want to look at the limit of this when A goes to 0, you have something that simplifies a lot your life. Is that in your truncation procedure of the noise, hidden there is a martingale structure. So because all the jumps of the noise are compensated by a Lebesgue part, actually when you diminish A, the increments of the noise, they have mean 0. Okay, they are centered, and for this reason, your noise, it's a martingale. Okay, it's a distribution valued martingale. Okay, and distribution valued time reversed martingale, and the martingale structure is actually conserved when you consider the partition function, when you consider iterated integrals. So okay, it's only a local martingale because you're not sure that this has finite expectation, but this is not too much of a problem. And therefore, because it's a non-negative martingale, you know for free that it has a limit. So the only question you have to ask is whether the limit is non-trivial. And okay, the first big result I want to present is a necessary condition to have non-triviality of the limit. So in dimension 1, if you want, you have no condition, because the only condition you have is the one for existence of the noise. But this condition is not strictly required to define ZA. So it's okay. It's good that to state it here. Okay, if things okay. And in dimension 2 or more and more, you have a stricter condition. So you need z to the power 1 plus 2 over d times log z to be integrable at 0. Okay, and in that case, you get that the limit is almost surely positive. And actually, this convergence, it holds in LP as soon as the tail of your noise allows you to be in LP. Okay, so if you want, the only reason why this thing could be not uniformly integrable if ZA has infinite expectation for every A. Okay, so this is a sufficient condition for having convergence of ZA. It turns out to be also necessary, or almost necessary if you want. So it's necessary in dimension 1 and 2, in the sense that if it's not satisfied, then the limit is 0. In dimension 3, it's almost necessary in the sense that, well, actually, the necessary condition has an epsilon here. Okay, so the two conditions do not match. This log z to the minus epsilon, I think it can be log z to the minus 7. So, okay, things are very close by, but there is still a little gap. Okay, the third part of this result, if you want, is that the limit you obtained when it's non-trivial is a solution of the stochastic equation with multiplicative noise. Okay, so this gives you a right notion of solution and okay, kind of necessary and sufficient condition for existence. So it's not exactly that, but because we have not proved that when this limit is degenerate, you have non-existence. But okay, it's kind of reasonable to assume that this is what will hold. Okay. Okay, so so this was the first part of the talk. So let me summarize it a little bit and let me check time. Yes. So okay, so if you consider the stochastic equation with Gaussian multiplicative white noise, then you get a solution only in dimension 1. And the problem is not well defined in dimension 2 and 3, 2 and more. But if you consider a pure jump Lévy noise, then really you have a condition on the jump intensity, but which okay always allows for solution for some noises in any dimension. Okay, and this is not the first result of this kind. Actually, first work on this problem was by Saint-Loubervier in '98. But okay, our work improved on both on the sufficient condition and and there was no work on the necessary condition. And okay, the best condition that were known before, they were really non-optimal in the sense that even in the exponent in Z it was different. Okay, so I did not take the time to expose all the in detail all the previous conditions that were obtained. And also they had restriction on initial conditions, so it's also they couldn't treat the Dirac at 0 in condition, which is related to directed polymer. Okay, so now, okay, if you have a question, maybe it can be the right time. Now I will move back to the case to the question of scaling limit for directed polymer.
No, apparently there are no questions for the moment.
Okay. Okay, so so let me redefine directed polymer. I'm just considering the same model of directed polymer as before, but okay, because of okay, instead of considering an exponential, I consider a product of 1 plus beta eta. So if you want, if you fixed for a fixed beta, this would just correspond to a change of variable. We are going to consider betas that tends to 0, so it's a bit more than that. But this is really the right setup for which you can obtain a scaling limit. Okay, and it also looks like more like a discrete version of the stochastic heat equation, okay, because this is the effect of multiplicative potential. Okay, the idea is that if you choose eta with a certain distribution, well, okay, in the domain of attraction of something, and you take beta to 0, and you look at diffusive space-time scaling, you can obtain as the limit the solution of the stochastic heat equation. Okay, so let me give you more details about that, and first talk about the Gaussian case. So if you assume that your environment has finite second moment, so for simplicity, okay, I consider it centered with unit second moment, but this is no loss of generality. So in that case, it was proved by Albers, Hanin, and Questel that if you rescale beta by n to the -1/4, and you rescale space and time diffusively, then your partition function converge to the solution of the stochastic, to the point-to-point partition function of the stochastic heat equation. And okay, this convergence is of course only in law, okay, because things are not defined on the same space. And here I have a prefactor square root of n, which just comes from the local central limit theorem for the simple random walk. It has to be compensated. Okay, and okay, there is also a factor square root of 2 here, which comes from the fact that random walk only visit half of the site, so it kind of affects the intensity of the white noise you find in the limit. Okay, but in spirit, the thing is just okay. When you rescale this diffusively and you tune beta in the right manner, you obtain the solutions to the stochastic heat equation. So now what happens in the case where the second moment is infinite? Well, if you consider that eta as pure power tail, okay, so you could also put a slowly varying function here, but I didn't want to make the result too complicated. And here I'm not considering the case alpha equal to 1, but it's not really important. It's just also because you need some log correction in that case, and I didn't want to write complicated formulas. So if you take alpha basically smaller than 1 plus 2 over d, and if you rescale beta in the following manner, then by rescaling space and time diffusively, you obtain a similar convergence, okay, towards the solution of the stochastic heat equation. And here, okay, there is a typo here. Square root of 2 should be this 2 to the alpha minus 1 over alpha, which also, okay, comes from the same reason as the square root of 2 we had on the previous slide. Yes, so I guess this is what I wanted to say. Yes, no, an important remark here is that, okay, I say alpha smaller than 1 plus 2 over d, it can seem like a restriction. In fact, it's not a restriction, because if alpha is larger or equal than 1 plus 2 over d, this limiting object is not well defined, okay, because for alpha stable noise with alpha larger or equal to 1 plus 2 over d, our criterion before is not satisfied, and actually we know that this thing is equal to 0. Okay, the ZA would converge to 0, so this thing is not well defined. Okay, so the result is if alpha is such that the stochastic heat equation with alpha stable noise as a solution, then we have the following convergence. Okay, so this is the first remark here. And a second remark, which is important, is that here, for simplicity, I've just written the limit for one partition, well, okay, the point-to-point partition function. But actually, the result is much richer. What you have is really the convergence of a polymer measure towards a measure on continuum pass, okay, for which, okay, you have convergence of the discrete polymer model towards a continuum model for which the partition function is the solution of the stochastic equation. Okay, so this is good. I think I will have a bit of time to talk about localization of the solution. Okay, so what do I want to talk about? Okay, let me go back to the notion of point-to-line partition function. So the point-to-line partition function is just a point-to-point partition function integrating along space. So it's the total mass at time t of my solution. And we say that the solution is localized, okay, if basically this integral here is okay. You can recover the full mass, okay, almost recover the full mass if you just integrate along a small proportion of the space. So let me formulate here a conjecture, and then I will give some strong motivation for this conjecture. So what we conjecture is that as soon as beta is positive and when your solution is well defined, basically you can recover all this integral by only integrating on k balls of radius r. Okay, meaning, okay, if you fix epsilon, basically you can, with large probability, recover a probability, a proportion 1 minus epsilon of the integral by integrating over k of these k large balls. Okay, and of course, okay, this is just standard theory of integration if you think of this result for fixed t. Okay, of course, an integral, I mean, okay, if you take a large ball, you can get almost all the integral. The important point here is that this thing is true simultaneously for every t. Okay, so you don't need to increase k or to increase the radius you're considering to get all the mass. So even for a very, very, very large t, okay, you only need a fixed number of balls in order to recover almost all the mass. And of course, this is not true if beta is equal to 0, okay, because when beta is equal to 0, the solution is basically spread on a big ball of radius square root of t. So yeah, okay, so you cannot, this could not be true. Okay, so why should this be true? So to motivate this, I need to go back to directed polymer. Okay, I'm writing formula after 40 minutes of talk, so it's not a very good idea, but okay, need to introduce the notion of free energy of the directed polymer, and to be simple, this p beta is just the exponential rate of decay of the partition function over its expectation. Okay, so p beta is positive if z is typically exponentially smaller than its expectation, and it's 0 if it's not the case. Okay, so it measures how this thing decays on exponential scale. And okay, this P is very important for localization property of polymer trajectories. And okay, lots of people have worked on that in the last 20 years. Basically, the conclusion of this, okay, the finest result that has been obtained by in this direction was by Bates and Chatterjee. And what they proved is, okay, this thing, but what this thing means is basically they proved the Cesaro mean version of the conjecture I stated before for the, okay, they proved the Cesaro mean version of this result. Okay, so you don't have that this is true for every t, you have that this is true for a large proportion of t, if you want. The condition that they have for this to be true is that p beta has to be positive. Okay, and this condition is actually a true condition in the sense that there are cases where p beta is equal to 0. So actually, it dates back from the very beginning of the study of polymers. So just by looking at the second moment of the partition function, Imbrie and Spencer and Bolthausen, they realized that, okay, if your environment has finite second moment, and if beta is smaller than a certain value, then p beta is equal to 0. Okay, and this phase is called the weak disorder phase. And Comets and Yoshida, for instance, I proved that in the weak disorder phase, the trajectory, the distribution of trajectory converge to the distribution of Brownian motion. So you can't have localization of solution in that case. But it has been shown that in dimension 1 and 2, p beta is positive for every beta. So this contrasts with what happened in dimension 3. So this was shown by Comets and Vargas for dimension 1, and by myself in dimension 2. Okay, and not only this was shown, but actually you have asymptotics for the value of beta when beta gets close to 0. So beta behaves like p beta behaves like a power of beta in dimension 1, and like something much smaller in dimension 2. Okay, so now what is our result that kind of motivates the conjecture? So, okay, I'm not considering the same P as before, but morally it's the same. It's just that we have a problem with showing that the expectation of the log is finite. But okay, this P, it really measures the exponential decay of Z over its expectation. Okay, it's just that we define it with a square root instead of the log. And what we show is that this P is positive in any dimension for every beta. So it kind of contrasts with the directed polymer, where things are different in dimension 3 and more, and in dimension 1 and 2. Here, in every dimension, you have strong disorder in the sense that you have exponential decay of Z. Well, Z is always much smaller than its expectation. So this okay, I believe that using the tools of Bates and Chatterjee, there is some hope that at least on the Cesaro mean level, one could prove the localization conjecture. So yeah, it's just a matter. I think the method is quite robust, so it needs to be checked, and maybe there are some technical stuff to see, but okay, when we will have time, we will try to work on this. And maybe a last remark to conclude, okay, and which will kind of emphasize this contrast with directed polymer. Okay, contrast and also a similarity. The asymptotic in beta that we find for p beta, it's actually the same as for directed polymer in dimension 1 and 2. And for directed polymer, I mean, okay, because you have, okay, the fact that what you find in dimension 2 is not a power, but something that decays much faster, is explained by the fact that 2 is a critical dimension. So below criticality, you will observe power. After criticality, you will get 0, and in the middle, you will get this, something that decays much faster. Here, it turns out that in a sense, all dimensions larger than 2 are critical dimension, which is something which is a bit surprising. And okay, this is okay. In order to see this, you need some assumption on the noise, and here's the assumption we have is that the noise has finite second moments, so that you are really in the same class as the one we looked at for directed polymer. Okay, so okay, I guess this was a bit dense, but thank you very much for your attention. Okay, thank you.
Well, thank you, Hubert, for this very nice talk. So we are open for questions. So, well, maybe while people start thinking question, let me ask you, check whether I understood correctly what you present. So you mentioned that in higher dimension, under certain values of your parameters, what you get, it's well, the equation Z doesn't make you converge to some object which is trivial, and which is something which also happens if you take Gaussian white noise. But they are completely different, right? While you vanish in for Gaussian white noise, the objects explode. So though you have this same phenomenon, actually they are completely different, right? Is that correct, or I misunderstood something?
Okay, so okay, let me start. Okay, so it's okay. No, actually, it's a phenomenon. It really depends on how you look at things. So if you look at the okay, if you look at the Taylor expansion, you have something. Okay, positivity is not something which is obvious. But what you can do also in the case of Gaussian noise is okay, take your favorite decomposition of Gaussian space-time white noise. Okay, and from this you can construct a sequence of martingale approximation. Okay, so let's say you take your Gaussian white noise, you just keep the first few Fourier coefficient, and this gives you a kind of truncation of your noise. Okay, in that case, well, the formula is always well defined, it's positive, and you have a martingale structure. And the only thing wrong that can happen in that case is that you converge to 0. And this is indeed what happens in dimension 2 and 3 and more. So the phenomenon is actually the same. And so now the question is maybe when you have Lévy noise, can the same thing as in dimension 2 appear? And I guess in theory, yes, I wouldn't know at all how to prove this, but if you're, okay, if basically your condition is not satisfied, but it's not a matter of the power, but it's a matter of the log, then maybe by tuning the intensity down when you make A converge to 0, maybe you should find a non-trivial limit, but this seems, okay. This seems really
well, it seems to be a very interesting question, right?
Yeah.
And this, well, and the same line, I mean, the stochastic heat equation, it's maybe the building block to investigate these nonlinear SPDs. And so have you considered that, but with changing so white noise by Lévy noise?
Okay, so I would have to check back. So there is something quite important here, is that the Kohlhoff transformation to go from SHE to KPZ, it's not fully working when you have jumps in your noise. So at least okay, maybe you get something, but the noise you get in the end, it should be completely different. Okay, so for instance, the nice thing to, okay, the most natural thing to consider is alpha stable noise. But if you take alpha stable noise for the SHE, you don't get alpha stable noise for the KPZ you would get on the formal level, because somehow the log will act on the intensity of the jumps. So yes, I would say I would have to explore more this in order to say something meaningful about that. But yeah, I guess it's an interesting direction, but I don't know if our works, I wouldn't know if our works help towards this direction now.
And then another question is, well, so you define this limiting field, right? So have you investigated properties of this random field?
So
of course, here
so
at the moment.
Yeah, so there is one thing that we actually okay, so you can look at several things. You can look at the solution with Dirac initial condition, and you can look at the solution with at the solution with constant initial condition. If you look at constant initial condition, you have a field which is ergodic. Okay, the solution at time t, it's an ergodic field for every t. And in that case, the last result I presented about P, it gives you some localization result, but like non-quantitative, but it tells you that, okay, it tells you that basically the solution is really concentrated on a very small proportion of the space. So this is the kind of quantitative result we have. But there are other people that looked at this kind of thing. So there is work by Kosnevichan that looked at specific noises and and tried to understand the geometry of the peaks. And I think it was in dimension 1. And I know that Karsten recently worked on things concerning the asymptotic peaks of the solution. For the solution in the case, I think okay, it was in the case of general noise, but the result had a specific interpretation for alpha stable noises. So I wouldn't be able to state the results, but there are some things that exist in that direction.
Well, thank you. Are there any other questions? No? Okay, so if no more questions, well, thanks again, Hubert, for this very nice talk. And then we continue next week at the same time. So good week to everyone. Bye-bye.
Thank you, Claudio. Thank you to all the audience. Bye.
Bye-bye.